Thank you for your interest in our paper. I will present our work on robust fine-tuning using fast trainable projection. The process of fine-tuning refers to training a pre-trained network W0 on a different dataset, which is potentially much smaller than the pre-training dataset. Recent works find that naively fine-tuning a pre-trained model without constraints can lead to worse robustness, because the new model forgets the general knowledge acquired during the pre-training phase when feeding to the new dataset. The goal of robust fine-tuning is to fit the new data distribution while maintaining as much pre-trained general knowledge as possible. To avoid forgetting, the prior work, Trainable Projected Gradient Method, TBGM for short, proposes a constraint optimization problem. Specifically, on top of minimizing the training loss, TBGM imposes a hard constraint on the deviation of the model from its pre-trained initialization. TBGM's goal is to learn this constraint automatically and enforce it through projection for each layer in a neural network. However, TBGM suffers from heavy computational overhead, as it needs to run a nested optimization loop during each update. Moreover, it also requires a separate data loader and sampling additional data during each step, making it less modular than desired. To improve it, we propose Fast Trainable Projection, FTP for short, to improve computational efficiency and achieve better modularity. FTP removes the nested optimization loop and the requirement for additional data by combining gradient information from the previous step and the current steps. Specifically, FTP is an optimizer for fine-tuning. For every trainable matrix and a vector in a network, FTP maintains trainable projection parameter gamma, and it updates gamma during each iteration of optimization simultaneously with other model parameters. Here is a high-level illustration. During each iteration of update, in the first step, FTP makes an unconstrained gradient descent step just like other common optimizers. Then FTP updates its projection parameters using the previous and the current gradient information. Finally, it projects the unconstrained update towards the pre-trained model W0 using the updated projection parameters. Overall, each weight W will learn its own weight constraint. The strength of the constraint dictates how much the model is allowed to move away from the pre-trained model. The algorithm learns to use different constraints for each layer to fit the training data while also stay close to the initialization. On the right, we've shown an example of changing constraints for all layers in a ResNet 50. All constraints start from a small value and grow larger. Compared to TBGM, FTP is 35% faster and achieves comparable robustness on downstream tasks. FTP achieves this speedup by removing the nested optimization loop in TBGM. Furthermore, FTP can be easily integrated in existing optimizers, such as ADAM and SGD, because it removes the requirement for additional data in TBGM. It is also easy to use with no change to the underlying applications. Here's an example of using SGDP, which is an SGD variant with built-in FTP in PyTorch. All we need to do is to specify some optimization parameters, for example, excluding the model heads from projection. Then we can initialize and use an FTP-enabled optimizer just as usual. In this example, we fine-tune a CLIP VIT base model on ImageNet and report performance on ImageNet and several ImageNet variants such as ImageNet adversarial, rendition, and sketch. Compared to vanilla fine-tuning, fine-tuning with FTP not only achieves the best performance on ImageNet but also on other variants. This shows that FTP not only fits the new dataset but also retains more knowledge from the pre-trained model. In summary, We proposed an optimizer FTP that can be easily integrated into existing optimizers to help mitigate forgetting during training. Thank you for listening.